Yeah, Dhanush, you can start now.
Yeah, thank you, sir. Greetings to one and all present here for an IEEE International Robotics Workshop. I am Dhanush B, IEEE Student Secretary of Robotics and Automation Society from the Department of Electronics and Communication Engineering. On behalf of St. Joseph's Institute of Technology, I am here to volunteer for today's session. Now, I would like to extend my first and foremost gratitude to our Honorable Chairman, Sir Dr. B. Babu Manogaran, our Managing Director, Mrs. P. Jessipriya Ma'am, and our Director, Sir, Mr. B. Sashishekhar, and our beloved Principal, Dr. B. Ravichandran, Sir, for giving his opportunity to conduct the webinar. I would also like to extend my gratitude to our Head of the Department, Dr. C. Jnanakausalya Ma'am, Staff and Student Affairs, and Dr. G. Rogini Ma'am, Lab Affairs, for their ceaseless support. Now, I will be sharing a few words about our speaker. Our speaker of the day, Dr. ZEID KOOTBALLY, received his PhD in Computer Science in 2008 from the University of Burgundy, France, for a dissertation on moving object predictions in dynamic environments for autonomous ground vehicles. He is currently a senior research associate with the Department of Aerospace and Mechanical Engineering at the University of Southern California, USA. His research interests are in automated robotic systems. He is specifically interested in knowledge representation and task planning for agile industrial robotics. Prior to his current research efforts, Jade worked on modeling a level of situation awareness for autonomous ground vehicles to they are able to plan a path while avoiding any collision with static and moving objects on the road. Jade has also helped in the evaluation and conception of test methods to measure the technical performance of devices used in the ASSIST, Advanced Soldier Sensor Information System and Technology Program, and DARPA, Defense Advanced Research Projects Agency Research and Development Project. Dr. Jade has also received many awards for his dedication and his hard work. Before we start the session, I would like to say few instructions to be followed by the participants. Kindly post your questions in the chat box. There will be a question and answer session at the end of the webinar. The attendance link will be posted at the end of today's webinar. Now, I invite our speaker of the day to kindly start the session. Sir,
Yes, thank you. That was a very good introduction. So should I start?
Yes, sir, please.
Okay, thank you, because I heard some people talking. All right, so thank you for the introduction. That was very good, I would say. Okay, so today's topic is ARIAC. ARIAC is an acronym, and we will see what it stands for. So we will talk about ARIAC, which is a simulation-based competition for industrial agile robotics. As mentioned, my name is ZEID KOOTBALLY. We will take a look first at the topic for today. We will take a look at simulation in general and then simulation in robotics. So the idea here is to get you interested in simulation, to see what exists out there on simulation, especially in robotics. Simulation has been created for a reason, and we will see the role of simulation, the advantages, and also disadvantages of simulation. The fields of robotics that are using simulation, there are many, and we will take a look at some of them today. Also, simulation software is a very part of using simulation in robotics, and we need to take a look at the available software out there and how to choose the correct one. So I will try to make this section interesting with some videos that I took from YouTube, and the links will be provided in the slides as well. In the second part of this presentation, I will talk about ARIAC, basically why we have created ARIAC, take a look at the competition itself, what it is about, and also the different challenges that we are trying to address in ARIAC. Okay, so as mentioned before, I will try to go very quickly on this slide because the introduction already talked about most of it. I am from USC. This is my current employee. I have been a guest researcher or associate at NIST from since 2015, I believe. My interest, well, I worked a lot in autonomous driving using simulation. And the name of the application was PRIDE, Prediction in Dynamic Environments. And then we moved to industrial robotics a few years ago. My main interest is basically in knowledge representation, how you represent information, and we use ontologies, which are basically a way to represent concepts and the relations between concepts. And we also have interest in the graph database. This is a database where you can basically see nodes very easily. This is not a relational database where you have keys, etc. It's easy to visualize, it's easy to understand, and we have converted ontologies to graph database, and we are doing this currently at work for pick and place operations. I am also interested in task planning. We've been doing lots of work with the planning domain definition language, PDDL, basically to do task planning for robots for pick and place. And more recently, we have started to work on autoencoders for 3D pose estimation. So basically you have an object in the environment. The camera sees only part of the object. So the idea is to be able to basically estimate the pose of the object, even though it's partly occluded. And we are using autoencoders for this. Okay, before we talk about simulation in general, I would like to go through this slide, which describes basically a brief history of simulation. Simulation has been recognized as an important research tool since the beginning of the 20th century. But it's older than that. For example, in ancient Rome, military were trained by sparring in mock battles using training weapons. So the purpose of these battles was not to injure the opposing side, but it was used so that individuals on each side could gain significant combat experience. Experience from simulating battle provided the Roman army an important advantage over any other army. And many believe that having this kind of simulation in the military contributed to the rapid expansion of the Roman Empire. The other example of, a good example of simulation when we talk about simulation in history is the link trainer, also called the blue box or pilot trainer. This is the world's first commercially built flight simulator. It was built by Edwin Albert Link in around 1930s. So then more than 10,000 blue boxes were produced during World War II, and they were used as standard equipment at every training school in US and allied nations. So they have some experience using this kind of simulator. Simulation was boosted to new levels with the development of computers. First, the analog computers and later the digital computers have boosted simulation to new levels, and we will see what we can achieve with simulation nowadays. Okay, if you want a formal definition of simulation in the context of robotics, this is one of them. This is one good definition, I would say. This is the process of designing a model of an actual or theoretical physical system, executing the model, and analyzing the execution output. Simulation is very common in our lives. For example, to understand reality and all of its complexity, we try to build artificial objects and dynamically act out roles with them. So I am sure that all of us have come across with simulation very early, namely playing a game in our youth, for example, being a parent, playing with your siblings as a doctor, fireman, etc. Is just a simulation where a child is playing a role in a virtual environment with toys. The principle of learning is essential in simulation. Using simulation, we can learn about something in a very effective way. And while modifying rules, we can observe the effects of our interaction. Simulation opens a wide range of options for solving many problems creatively. Okay, so let me take a look at the next slide. I will be I'm sorry. Yeah, I had some noise. So in this slide, I'm going to basically discuss the advantages of simulation. Of course, simulation is not perfect. It has some advantages, and we will also see the disadvantages. The simulation is very good at studying the behavior of a system without building it. It's a cost-effective approach if you want. You can design, visualize, and test an object even if it does not exist. And this is one of the power of using simulation. You can even see the results of a system that hasn't been built yet. It also helps you to find unexpected phenomenon and behavior of the system. It is possible that your solution may fail or even blow up, but only in simulation. Okay, so when you see something that goes wrong, you can rectify this. There is no harm that will be caused to people because we are using simulation. So basically using the simulation tools, one can avoid injuries and damages. Unnecessary changes in design after the production of parts has already started, and too long cycle times in manufacturing process. Simulation enables us to work even in 4 dimensions. For example, you can, I would say, observe within a few minutes how a planned production will be realized in next month. Okay, we have some very good simulation software and tools that can predict what can happen in a few months, in a few years, just by using these tools. You can also speed up a process or slow down the process to observe all the details in a different way. And all of these make things, I would say, easier and cheaper. Okay, you do not have to build a physical system. Sometimes you do not have the facility to build a work cell, and you can do this in simulation in a few months. There is also the what if analysis questions that you can easily perform in simulation. One of the problems in classical design and planning are what if questions. Many of them are due to the system complexity of an often unasked or not answered. But with up-to-date simulation tools, one can deal with exact geometry, consider the dynamic characteristics of a system, or for example, include the human-machine interfaces, visualize object in 3D in detail. So having all these in mind, there is no reason for avoiding any what-if question. So the boundaries of what is possible or not are pushed far away, especially in advanced virtual reality tools. Using simulator, researchers may build experimental environments according to their own imagination. When I talk about imagination, this game here comes to mind. This is No Man's Sky. It's a game, basically an exploration game. And the worlds or the different planets are built using procedural generation. And you will see the details that come with this game is pretty amazing. And we can push the boundaries using simulations. This is another topic where we can use simulation without harming people. Simulation in medical field, for example, you just simulate an operation, and you do not have to test this on real people, which is pretty good. All right, so those are some of the disadvantages of simulation. I have 3 on this slide, and there may be more. It depends on the type of simulation you are using, but it can be expensive to build a simulation model. it takes time and people to build a model. For example, you build a simulation model. I'm not talking about robotics yet, but in general, let's say you build a model to predict how your stock markets will move in the next few months. So this requires lots of knowledge, lots of data, etc., to be able to analyze this kind of predictions. It can also be expensive to conduct simulation. Basically, you need people again, and also you need sometimes you need a very good software, sometimes expensive software to work with the simulation. Not all the simulation tools are free, unfortunately, but the good ones are free, but the best ones, maybe you need to purchase a license. And also, I guess this is the third one is, for example, I would say uh, the most important disadvantage that we can cite when we talk about simulation. This is about validation. So validation requires data. So you have something working in simulation. How do you know it's going to work in real life? Okay, so you need to validate your models. So simulation is an excellent approach to analyze problems when the available data is limited, since no data is necessary to construct a simulation. Validating a simulation, however, often requires multiple data sources to achieve a great degree of confidence in its representation of real-world dynamics. So basically, the process of validation is a disadvantage for simulation when comparing it to data analytics approaches, since validating simulations is often more difficult. So you do not need data to build a simulator, but you need data to validate your simulation. So for example, this is an example here of traffic simulator. So basically, by the way, all the blue links you see here, there are links to the website. I may have missed, so there's a link here as well, so you can take a look at those websites. So I was talking about simulation of traffic on the road. If you want to build a simulator like this, we would not need any data to start. Okay, so you just need a way to build the roads, a way to put traffic signs in your simulator. And you have some sliding bars here where you can modify some parameters. But this is basically just a kind of a dumb simulator that will allow you to show cars driving depending on the parameters you set here. So we could construct a simulation that incorporates modeled cars, driver behaviors, and road conditions, and that's it. You have a traffic simulator. Analysis of this traffic simulation could provide surprising insights, such as the pattern of traffic jams migrating in the opposite direction that automobiles are traveling, for example. So to test such insights and to make sure they are valid, we would need to use various data. We would seek information about road conditions in a range of contexts, for example, in cities, highways, in specific countries, US or other countries, India, for example, and under different weather conditions. We can then recreate all of those scenarios within the simulation and see how well they match what actually happened in the real world. Okay, so simulation is not just putting stuff together and run. You need to have data in the background to make sure that your simulation works as it would in real life. So, and this is a disadvantage because finding those data is sometimes very difficult, depending again on your application. And sometimes it's very easy to find those data, but you need a way to integrate those data in your simulator to be able to mimic or to replicate real-world applications. Okay, now we're moving a little bit towards robotics, which is the main topic of this presentation today. Robotics is a very interdisciplinary and a fast-growing research field. Robots are introduced in various areas and used for different tasks. Also, the requirements for the simulation tools depends on the particular application. However, all new applications, methodologies, and technologies in robotics share the requirement to simulate robot systems and the environment with sufficient sophistication and accuracy. So accuracy and sophistication are two very important factors when you build a simulator for robotics. In the next few slides, I will describe the use of some simulation tools in some robotic fields. I said some of them, but I'm not going to cite all of them because otherwise I will not have enough time to talk about all of them in this presentation. And also I will try to make this interesting with some videos. So the first type of simulation for robotics we have is to simulate humanoids. So advances in humanoid robotics open new possibilities of introducing humanoid robots into human environments. The goals of this emerging technology is that robots will work, assist, entertain, and cooperate with humans, or do certain jobs instead of a human. We already have robots helping people in manufacturing environments, but they're not humanoids. They are industrial robotics, but people or researchers are working towards using humanoids to help human in their work. Some areas such as service robotics. You may have seen some videos in Korea or Japan where they use humanoids to help people recover from some situations, mental situations, for example, or physical situations where they had an accident, and they use humanoids to help people coping with the situation. So virtual worlds, dynamic walking, and haptic interaction. Haptic means that is related to the sense of touch, in particular relating to the perception and manipulation of objects using the senses of touch. And yes, with we have some sensors nowadays on robotic hands, and you can feel objects. You can know if an object is slipping away in your hand, for example. And humanoids, robot work in those fields. So I'm going to talk about a work that, well, the use of robotics and also humanoids, mobile robots, industrial robots in RoboCup. RoboCup is an annual international robotics competition proposed and founded in 1996 by a group of university professors. The last iteration of RoboCup was last year, I believe, 2019. I forgot where it was held. I believe it's Australia. I may be wrong. But yes, it's a still ongoing competition. The aim of the competition is to promote robotics and AI research by offering a publicly appealing challenge. RoboCup comes with many different leagues. For example, you have the RoboCup Soccer Simulation League. You can use this league to basically promote or try to compete in 2D or 3D games, soccer games, I would say. All right, so this is the 2D version of the game. So you have to program your players, I would say, to play a soccer match. Okay, so it's 11 vs 11. Here, this is in 2D. I would say it's easier because you do not have to basically work on the joints of the robot. So let me try to zoom in here, expand this. So this is the 3D version. So things seem a little bit dumb. That was a good kick. You can see the robots moving, they're running, they're kicking the ball, and all of those actions need to be, be part of your program. And they usually fall like this, and they have to get up. It's a very interesting and also challenging, because now you have to move to be able to see the ball with vision in simulation. You have to know when to kick the ball, for example. And the 2D version, as I said before, is a little bit easier. You have some balls, if you want, for the players. I'm not sure where the ball is in this. It's here. So it's a bit easier to simulate, I would say, the program itself to write, but it's also very interesting and challenging to come up with solutions for this kind of game. And if you want to take a look, not in simulation, but how RoboCup is, Robo Soccer is done in with physical robots, and this is an example here. I think it's a 2v2 game. It may take a long time for robots to be able to kick the ball, so they need to use vision to be able to see the ball. They need to understand how to go to the ball, and then they need to know when to kick the ball. Okay, basically, if you are here, you are facing this the goal here, you have to kick the ball. The way I'm saying it seems very easy, but it is not. In reality, it's very complex, and it requires lots of things in the background. And I believe the score is for this patch here. So let's take a look at this one. Let's wait to see. Yeah, here we go. 7-0 for Nimbo. Okay, so we are using humanoids for in RoboCup, and I believe anybody can participate in the RoboCup competition. You just need to build a team, and work together. And of course, you have to travel to the places where the RoboCup competition is held. But I'm not sure what is going to happen in 2020. Maybe everything will be online or in the cloud. Need to wait. The second section I will be talking about when it comes to robotics is mobile robotics. This is a complex research area in which many advanced technologies and open research issues are combined all together. It is often difficult to master perfectly every technology, and hence realistic simulations and fast prototyping of mobile robots help reduce, I would say, it will help reduce the amount of time and hardware spent in developing mobile robotics applications. Moreover, simulation tools allow researchers and students to focus on the most interesting parts of their robotics projects to achieve more advanced results. When I started working at NIST in Gothenburg, I worked on a simulation tool called, I believe, USASIM. With this, I was able to simulate on-road driving with vehicles. Okay, so for this application, I only focus on path planning and navigation. And when I presented my work to conferences and workshop, for example, people would always ask me, how did you do the sensor part? And I would tell them that I did not focus on the sensors, but only on the planning part. So, excuse me, sorry. So basically with mobile robots, you can choose which area you want to focus on. Maybe it's sensor processing, maybe it's path planning, maybe it's navigation, maybe it's mapping, maybe it's localization. So it's very important to choose with part of the robot you want to work, and you can have a team with multiple people working on different areas on your mobile robotic application. Especially as mobile robots move out of labs and into the hands of users, it is required that simulation tools provide an integrated development environment for specifying, evaluating, and deploying robot missions. Furthermore, integrated support for evaluating solutions via simulation and finally deploying them on robots must also be available. Okay, so simulation allows you to focus on certain areas, test over and over what is going to happen with your robot in simulation without, again, having a real robot at hand. Especially with the lockdown, sometimes you do not have access to physical robots at universities or at your work. And simulation is a way to be able to keep working while not physically at your workplace. So again, I'm going to talk about RoboCup, and this is another league. So we saw the soccer league. This one is called the Rescue Simulation League. This competition involves, so it has two sections or subsections. The first one is agent simulation competition, and the second one is virtual robot simulation competition. So the first one involves the evaluation of the performance of agent teams developed using the ADF Agent Development Framework on different maps of the RoboCup Rescue Agent Simulation platform. Specifically, it involves evaluating the effectiveness of ambulance, police force, fire brigade agents on rescuing civilians and basically, for example, extinguishing fires in cities when an earthquake has just happened. So the RoboCup Rescue Simulation League brings people with ideas, who have ideas on how to use simulation to rescue people trapped, for example, in a disaster. You know, you have an earthquake, people are trapped in a building. So the building collapsed, people are trapped. Now you need to find those people, okay, rescue them. And we are trying to do this in simulation first. And the first one, agent simulation competition, this one here, allows you to basically develop some algorithm to move firefighters, ambulances effectively in on a map. Okay, so you know, getting some ideas, getting some algorithms from people, some approaches on how to do this. The other one is, I would say, a little bit more fun because you use 3D models of robots. Again, you can. The idea is to release robots in a collapsed building or an earthquake damaged area instead of using people or firefighters to look for the victims, because you know you can get crushed by some part of the building collapsing on you. So even though robots are very expensive, the idea is to send robots instead of humans, and we can test you know, the path planning, navigation using simulation. You do not have to send your robot in a physical environment. For example, you can use SLAM, which is a simultaneous localization and mapping. SLAM is basically a way to build a map of the environment using, I would say, localization, for example, like AMCL, and also, let me zoom in like here, and also laser data. So this is being done in simulation where, you know, you send a robot in simulation is going to scan or map this area using laser data. And you can see the laser data here in red. I'm not sure if you won't be able to see it from where you are, but the red dots here are the laser data detecting objects. The blue parts, sorry, the white parts are available areas. The black ones are obstacles, for example. So you send a robot in an environment like this. Okay, imagine you send a robot like this in a real environment. It will build a map of the environment. And then afterwards, you can send your robot to navigate the environment to look for people. Okay, so mapping is part of the simulation, is one aspect of simulation that we use a lot for not only looking for people in or rescuing people, but in some other areas. This one is, I guess, a little bit more interesting for the youngsters out there. So this is also the Rescue League, but it's for this is the Junior League, I think. Again, you have to rescue people, but in a more, I would say, fun way for kids to learn how to use robots and how to program robots effectively. And I guess it's a little bit more attracting to the youngsters. Okay, so the other field is medical robotics. The introduction of simulation into robotic surgery is recent and advancing quickly. This has created the need to identify systems that effectively improve these unique surgical skills. The modeling of deformable organs, okay, you can work on a people's heart, for example, or lungs. These are deformable organs. When you push on them, they will deform. So the modeling, the planning and simulation of robotics procedures, safe and real-time integration with augmented reality. This is also one aspect of robotics we use. This is augmented reality. And all of those are key topics in the field of robot-assisted surgery. Just a quick try to find the right spot where it shows simulation with robotics. So basically, this is a way to do something in simulation and try something new in simulation and see how it goes. And if everything works fine, you can get some data out of this and try to implement it yourself in real situation. So robotics, as I said before, or simulation, sorry, allows you to break things without actually breaking physical things. So it's fine to break things in simulation. And of course, we have industrial robotics. Without simulation, we won't be able to do much in industrial robotics. When it's time to program an industrial robot on the production line, okay, so your robot is doing something like picking, I don't know, some boxes in the production line. Okay, the shift is over and you want to program or reprogram the robot to do something else, picking up apples. I'm just making up new stuff here. Okay, so instead of picking up boxes, you're going to start picking up apples from a conveyor belt, for example. Well, if you want to reprogram the robot this way, you usually have to stop the production line. And this downtime can cause upwards of thousands of dollars. And this is where offline programming comes in. So offline programming, OLP, is an attractive option for many manufacturers. Using simulation software, it is possible to digitally recreate robots, tools, fixtures, and the entire cell, then define a program complete with motions, tool, commands, and logic. That program can be processed and downloaded to the robot. So basically, instead of stopping the robot, the physical robot in your factory, well, you can do all the testing, all the reprogramming offline using a software or a simulation tool. Then you just need to download this software to the robot. Okay, it would be faster and you do not have to, lose money by stopping the production line. Now, choosing the right robotic simulation software involves several important considerations. Here I am focusing on industrial robotics, but the same questions apply to the other types of robotics I talked earlier, such as mobile robotics, medical, etc. Now, some of the questions we should ask ourselves when it comes to choose a robotic software. Will the software be compatible with the robots and tools in use? Is the software best suited to the process such as arc welding or painting? How much robot programming or CAD experience is required to use the software? And also, maybe the most important one, how much will it cost? As I said before, all not robotics simulation tools are free. Some of them are proprietary. So maybe basically you need to purchase a license to use for your robot. Some of them are free, such as ROS, Gazebo, etc. So I have listed some of the industrial robotics software available out there. This is not going to be an exhaustive list at all. Okay, I just listed 4 of them. If you do a quick Google search, you will be able to see many more. But I tried to list the most interesting one. I have to say I'm not affiliated with any of those companies. I should have a disclaimer. I should have had a disclaimer at the beginning talking about this. But yes, just some examples here. So the first one is Visual Components, which is an advanced, well, this is a software from Finland, and this is an advanced design and simulation suite for production lines. Entire manufacturing processes can be simulated and analyzed, including robotics equipment, material flow, human operator, action, etc. I'll have a quick video on what it looks like actually in the simulation. So you can basically simulate your factory floor with many other components. RoboDK is another one. This is very known for the offline programming aspect in industrial robotics. So this is used for to allow for scripting using Python or creating programs visually, thanks to its integrated 3D simulation environment. All programs are automatically converted into robot-specific languages before uploading them to physical robots. And one of the aspects of simulation I didn't talk about is that, you know, each robot brand has its own language. Okay, a robot from the FANUC manufacturer uses its own language. A robot from ABB, for example, uses its own language. And if your lab or your manufacturing floor has many robots from different brands, you will need to write an application for each of those robots, because you cannot have one language for all the robots. And simulation is a good way to test these new languages that you are moving to your robots. At work, we have something called CRCL, the Canonical Robot Command Language, which is a tool that brings, so you write the program in one language, and CRCL will be able to translate the language you use to the robot language. Okay, you have to do the mapping only once, and then you can use it whenever you want. And this will save time, and you can do testing in simulation as well pretty easily. Okay, 2 more before we move to ARIAC. So the next one is, oh, I guess I'm running a little bit late. Okay, the next one is Robot Studio, development suite created by ABB, and I'm not sure this is free. And the last one is Gazebo. Gazebo is the one we use in ARIAC, and we're going to move to ARIAC right now. Gazebo is free and it has a full integration with the ROS. All right, so we are in the second part of this presentation, and I will talk about ARIAC, which stands for Agile Robotics for Industrial Automation Competition. So we usually say ARIAC competition, but it's redundant because the C in ARIAC stands for competition, but just saying ARIAC seems weird, so we say ARIAC competition anyways. So the goal of ARIAC is to test the agility of industrial robot systems. We will see what agility means in a minute. So with the goal of enabling industrial robots on the shop floors to be more productive, more autonomous, and to require less time from shop floor workers. So basically, we were approached by small and medium manufacturers in the US who are struggling with some aspects of robotics. And they need a way to test that the robot will be able to do some robotics application. They need a way to see the challenges and see if their robots can do those challenges. So I guess the best way to do this is using a competition or simulation. And this is what we did at NIST. ARIAC is a simulation-based competition, so everybody can access this competition. It's free. NIST has teamed closely with OSRF. OSRF created or developed the first 3 competitions, and NIST, that will be me, somebody else, and other team members developed the last iteration of the competition that finished, that ended this year in May. Okay, so year 4 of the competition just ended. That was in May this year. This is a prize competition, so you do not need to pay anything to enter, but you can leave with some money. So the first one got 10,000 US dollars. Second one, second place, sorry, 5,000. Third place, 2,500. So anybody can participate in ARIAC, but you need to have at least one US team member to be able to claim the Va-t'en! Il recharge le téléphone, maman. All right. Sorry about this. All right, so 50, 60 teams registered each year. And this year we got many more teams. I guess it's because of the shutdown. People maybe had more time to work on this competition. And usually we have 4, 6 teams that make it to the final each year. All right, so ARIAC focuses on kitting, which is the process of gathering required components for assembly. And this is a kit. Well, actually, this is not a kit. This is these are the bins where you will pick up parts and put them in a kit. Okay, so we do kitting. We also did order fulfillment, receiving, processing, and delivering orders to end customers. ARIAC comes with agility challenges. We originally identified 30 agility challenges. That would be things that companies struggle with their robotic applications. Okay, there were 30 of them. So we talked with industry, we did literature reviews to be able to understand all those challenges. Then what we did is to rank each challenge based upon 3 criteria. The first one is industry's perception of how critical the challenge is. So you ask industry, so among those challenges, which one do you want us to take a look at? Which one is very important to you? Then the second criteria is how difficult the challenge is based upon perceived team capabilities. That would be the people competing in ARIAC. You should also ask them if they think it's easy to implement a solution for those challenges. Okay, so you need their feedback as well. And the third criterion, I would say, is to see how difficult it is to implement in gazebo. Okay, so we need to take into account the 3 things and then find a sweet spot between these things. And then you can implement them in simulation. And we came with 6 challenges: drop part in process kit change, sensor blackout, faulty parts, flip parts, and moving obstacles in ARIAC. Competitors in ARIAC basically split 50-50, I would say, educational institutions and also industry. Most of them are small and medium manufacturers. We have had many, I would say, teams from educational institutions and from industry. And 2 teams work with high schools STEM students to teach them robotics. At least 2 college classes are being taught around the competition. So we are teaching at UMD, we are teaching a class revolving around ARIAC, and each year we we modify this class. So I'm going to show you some videos about quick videos about some ARIAC challenges. Just wanted to talk about some terminology here. We have agility challenge, a task designed to be challenging for participant system. We have an order or a kit. Okay, I already talked to you about a kit. A kit is basically an order in which you will put parts and deliver those parts. Then you have trial, which is a single run of the simulation in which one or more orders are assigned to a participant system. Then you have a scenario, a high-level grouping of trials. So a scenario has multiple trials. One trial may have one or more orders, and one order and one trial can consist also of one or many challenges. Okay, so this is basically the structure of a competition. When you write your software will need to start the competition by issuing start competition command. Then you will receive an order. So the order will ask you or your system to build this kit, for example. What happens next is you do pick and place. You would have to tackle low-level challenges and high-level challenges. When you are done, so when this is ready, you deliver the kit. So this AGV here will go away and come back with an empty tray for the next order. Then you end the competition. Okay, so this is a flowchart visualizing what is happening in ARIAC. I mentioned low-level challenges and high-level challenges. So low-level challenges consist of how the robot interacted with parts. Parts were dropped or revealed to be faulty while attempting to finish orders. In some cases, a robot's team might be able to reach the drop part or find another part of the same kind that is not faulty. High-level challenges, some examples, your team may receive a request for a particular order and then receive another higher priority order. So this requires the teams to stop building the current order and to start working on a new order. And this is a very difficult challenge, as I would show you in a minute. So we had some trials, we had some scenarios in the last ARIAC. Each team is only allowed one control approach. Therefore, each team's entry had to be capable of automatically replanning itself based on the changing environment. And this is a good example of agility. With this one approach, you should be able to tackle all the trials, all the different challenges. And this is, I would say, the challenge of ARIAC. So this is the part we are using in ARIAC. In the previous versions of ARIAC, we only had gray parts, and this year we included colors. So for example, you can ask a team to fetch, well, to build a kit with 3 pulleys, so 1 blue, 1 green, and 1 red, and 1 blue disc. So the robot will need to find those parts in the environment to build the kit. The simulation architecture, this is basically an overview of the work cell. So you have some shelves on which you can put parts, you have bins, conveyor belt, automated guided vehicles. This is where you will build your kits. And you also have moving obstacles. We have 2 here. They can make some very interesting challenges. If you want to have a quick overview of what is happening in the work cell, you have people moving. Okay, so robot is here, AGV is here, another AGV is here, you have bins, you have shelves. And I don't know if you can see here, but we have some blue parts on the shelf here and some red parts here. Okay, so it's not a very, I would say, beautiful environment, but it's quite complex, have many factors, many components, and you need to navigate through them. The simulation architecture we use is a gazebo environment for Agile Robotics, which we call GEAR. GEAR-based system and tools are used by teams participating in ARIAC. If you participate in ARIAC, you will have to use this interface here. We have the ARIAC server. This is where we run the simulation, the trials, etc. We have plugins. You have a plugin to deliver tray. You have a plugin to control the cycle of the parts on the conveyor, for example. Control how we move parts. All the challenges are controlled by plugins. Teams interaction with the ARIAC server was via the GEAR interface. This is basically a ROS-based interface. So we provide ROS services and messages so you can communicate with the system. Okay, so you can, for example, send the AGV away when it's ready. You can query orders. So which order should I build? You can query or get information about on sensors using services. And all of those are available to you. You just need to know how to use them. A quick overview of the simulation architecture. So you are going, if you are a participant, you are going to provide a file with the sensors to be placed in the environment. We are going to parse this file for you. Then we are going to parse another file, which is basically the challenges for the competition. Where to put parts in the environment, where are people moving in the environment, and all of these are defined in this file here. Then everything is happening on the server. Okay, so the server will send you orders to build. When you're done with the orders, you will send these orders to the server. You will deliver the trays. The challenges are handled on this side. The trial scoring is also handled on this side, and data and console logging also handled on this side. So developer side, you only need to provide this file here and your code, and we will do the rest. Okay, so about sensor, this is a list of sensors we had available in ARIAC, and in your file, you will need to provide which sensor you want to use and where to place those sensors. Okay, so we have the brake beam sensor, for example. This one is just going to tell you when an object breaks the beam. So, okay, so this is a brake beam sensor here. There's a beam here. If an object breaks the beam, it will tell people. We have the laser profiler proximity sensor, tell you how far an object is from the sensor. You have RGBD camera, depth camera, logical camera, etc. So you can use any of those sensors, as many as you want. However, each sensor has a cost. The best sensors are the most expensive ones. And the cost here will play a big factor in ranking you at the end. Okay, if you use less or less sensors and cheap sensors, and you give some good outcome, then you will rank higher than somebody that is using very expensive sensor, for example, and give the same kind of outcome. This is how you would put sensors in the environment, just a text file, a YAML file, the name of your sensor, the type of the sensor, and where you want to put the sensor in the environment. Okay, location and orientation as well. And this is what you will provide to us. Okay, so the next thing is to quickly talk about is about the robot we use in the past ARIAC. This is a 15 degrees of freedom gantry robot. I'd say quite complex robot, I would say. So we have some rails here. So there's a small rail and long rail. So the robot will be able to move on those rails. There's a torso base which moves on the small rail like this. You have a torso main which rotates around the torso base. You have a robot tray where you can put parts. You have two robotic arms mounted on this torso, and you have a vacuum gripper at each extremity of the robotic arms. And we created this robot for only this year. And just an example of what you can use in ARIAC to control the robot. You can move the robot, you can control the joints, you can get information about the state of the robot, basically the torso, the left arm, the right arm. So, and again, all of these are provided to you. You just need to know how to use them. Okay, so we're going to take a quick look at each challenge, and then we will finish the presentation. So the first one, I will not go through all of them because I don't think I will have enough time, but I would like to take a look at some interesting ones. This is one of the challenges. This is called faulty gripper. So this is simulation, right? So you can simulate anything. In this case, we're going to simulate a gripper becoming faulty at specific locations. And usually we do this above the AGV. So you see there's a robot here. There's a part in the robot hand. The robot is going to place this part in the tray. However, we're going to simulate a faulty gripper. That is, the part will be dropped before it reaches its destination. Okay, so we are going to drop this part on purpose in the tray in the wrong spot. So the system, the team system, will have to reposition the drop part or use another part in the work cell. Let me see if I can run this. So I'm going to pause here. So the part is here, the blue part, and the robot is going to put the part somewhere in here. You will see that the part being dropped like this right here. Okay, it's kind of like, all right, so we kind of dropped it here. There is a sensor here which is telling the robot that this is a wrong location. What happens is that the robot will go pick up the part and put it back in the correct pose. And this is one of the, I would say, easiest challenges in ARIAC, as long as you have this sensor here. Okay, so it's repositioning itself to press the part correctly. So note that if you do not place the part correctly in the right position, you do not get all the points. Excuse me, are you still here? Yes. Okay, sorry. Yeah, we got some Zoom message saying that the screen stopped sharing. You still see my screen?
No, sir, your screen is not visible. Could you please try sharing it again?
Yeah.
Yes, sir, it's perfect. Thank you.
Okay, thank you. Okay, faulty part, I will not go through this one. Faulty part is basically, this part here is faulty. That is, it has some faults and it needs to be removed. You should never put a faulty part in a tray and deliver it. So basically, you get rid of this part and go back in the environment, find a new one. Okay, I'm not going to run it because if I run this, it's going, it looks like it's going to kick me out of Zoom, but those slides will be shared with you. The other one is called sensor blackout. So all sensors stop working. Okay, so we can decide, again, this is simulation. You can decide when to stop sensors to work and which sensors stop working. So you can decide this and all the sensors will stop reporting data, meaning your robot will have to work blindly or with recorded data, not with live data. So the idea is to keep the robot working while the sensor blackout is happening. So all the sensors will stop working. After a while, they will come back live. Part flipping, some parts need to be flipped. I will try to show you this video here. This is how you flip a part. We usually ask you to flip this big guy here, which is a pulley part. It is in the yaw of the part is not correct. So you have to flip it if you want to get full points. All right, so you have a high priority order. And I will focus on this one before I finish here. Let me try to go in presentation. Okay, I'll be back. It looks like I was kicked out again. Let me try to connect. Okay, should be able to see it now. So the last one, which we implemented this year, is called moving obstacles. Some scenarios include human workers going back and forth in a straight line between eyes. The workers will pause for a brief moment when reaching each extremity before moving again. Now, the participant system are aware of the possible locations. There are 4 possible locations, but they do not know where those obstacles will be spawned in the environment. The travel time and idle time for moving workers are not communicated to participants. Colliding with a moving obstacle sets the final score for the current trial to 0. Okay, you do not want to collide with any of those moving obstacles. So the idea here is to spawn 2 people in the environment, so they will either move this way, well, in this aisle, or in this aisle, this aisle. So you have 4 possibilities. Okay, people do not know where they're going to be spawned. in the environment. Okay, it can be one of these four. We don't know which one. We increase the level of complexity or difficulty by adding some parts here. So the robot is here. This is the top view. The robot is here. It will need to come somehow. We need to come here and pick up some parts here. Okay, so it needs to avoid this guy and this guy. Otherwise, you will get a 0 if you collide. This is another configuration. One is moving in this aisle, one is moving in this aisle. This is aisle 2 and 3, and this is aisle 2 and 4. Okay, you do not know beforehand where they're going to show up. So this one here is from Team Robot. This robot needs to pick up this part here. The only possibility is to go into this this aisle, but you can see that there's somebody like a moving obstacle here. So it needs to be very careful not to collide with this person here. Otherwise, you will get a 0. So now I'm not sure if it's a fluke or if it was intentional, but it managed to grasp this part without colliding with this person. Okay. The other one is from Team Versley. I will see if I can open this from here. If let me try this. Okay. So I sped up the video a little bit. No, this is not the moving obstacle, is it? This is another example of drop part, you see? Yes, it looks like I didn't open the right video, but that's fine. I wanted to open this one. Let me take another look. Right, yes. So I'm going to pause here. This robot needs to pick one of those parts. There is a moving obstacle in this aisle. The robot or the system does not want to go in this aisle. Okay, you have a big risk of colliding with people. However, you can reach those parts on this side of the shelf. And this is what exactly this team is doing. Okay, you can reach, so no need to go in this aisle. And when you're done, you're going to place the part in the tray. All right, I think this is my last slide. Almost. So I would like to thank everybody who contributed on this project. We have people from NIST, people from OSRF, the participants sometimes help us debugging some part of the code by submitting GitHub tickets, for example, and give us some advice, etc. This is a web page for ARIAC, and this is the GitHub for ARIAC as well for 2020. You are free to use ARIAC. You can modify it if you want. You can do anything you want. And that concludes my, I guess, my presentation. I'm sorry, I was maybe talk a little bit too much. Thank you.
Yeah, thank you, sir, for your stimulating and fruitful words. Now let's move on to the question and answer session. Okay, there is a question. How do simulation enhance research further?
Yeah, so simulation is a good way to test your algorithm. So basically, you can do fast prototyping in simulation. You can create something very quickly without having a physical robot at hand. And also having simulation, you can, if you have multiple simulation, you can test your application, your algorithm in one type of simulation, let's say Gazebo, and you should be able to do the same thing in other simulators such as VREP. So the idea also is to do or to modify as little as possible when you move from simulation to the physical applications. So again, testing algorithm very quickly, repeatedly. Okay, you can also come up with different multiple scenarios in simulation. Okay, so for example, this work cell here, if you have to build this in a lab, that may take you years. Now, if I just want to modify one thing, such as moving this bin from here to somewhere else in the environment, I can do this very easily in simulation, drag and drop in this case, and I can test my algorithm. And I guess this is one way where, well, one of the sections where simulation is very good at. Repeatability, testing procedures, and also validations, breaking things without breaking things physically, and also you can also modular or modify your environments as you wish, as often you wish.
Thank you, sir.
I hope this answers the question.
Yeah, thank you, sir. Here is the second question. Which one is the best workspace for mobile robotic simulation?
So which simulator is best for mobile robotic simulation? I would say, I guess, I hope this is a question. So if this is a question, I would say,
Yes, sir, yes.
Okay, thank you. The open source ROS Gazebo, I'm not sure if I have anything about this here. Yeah, I have an example with SLAM. Gazebo and ROS work together very well. And this is also, I would say, one of the best approach or best simulators to use when you are working with mobile robotics. It's free, it's open source, and you have many libraries already developed for you to do practically whatever you want. You just need to write some code, import those libraries, reuse those functionalities. But the good thing is you do not have to rewrite everything from scratch. You do not need to reinvent the wheels. The other one, I believe, is WebBots. I do not have much experience with WebBots, but it is available to you. And the third one I would say is from Microsoft. I forgot the name. I think it's Microsoft Simulator. But I will go in this order: Gazebo first, Gazebo and ROS first. ROS can be used with Python and C++. So it's up to you which language you want to use. You can also use MATLAB with Gazebo and ROS if you want. So ROS Gazebo first, then WebBots, and the third one would be probably the one from Microsoft.
Yeah, thank you, sir. And here is the final question. What is the good basic robotic simulator for a beginner?
For a beginner, so I'm not sure what is beginner in this case. What level? Do you have any like programming experience? So there is the simulator for the Lego. I forgot the name, but there's a Lego simulation when you can use Lego robots to, to go in a maze, for example, rotate left and right. I do not have the name in mind, but it's a Lego-based simulation. That would be the basic things I can maybe talk about. If you have some kind of programming experience, imagine you have Python experience, I would say definitely go with ROS and Gazebo. It's very intuitive to use Python with ROS and Gazebo, and you will learn a lot more with this application, this software as well. As I said before, the reason I'm always mentioning, not always, but most of the time mentioning ROS and Gazebo is because all the libraries that are available to you that you can reuse. Hopefully this answers the question.
Yeah, thank you, sir. Thank you for answering all the questions. I hope this would help them to develop in-depth of knowledge in this robotic simulation, sir. Now,
sure.
Yeah, thank
yes.
you.
I was just going to say that I'm available for question. I think you can see, you can get my email from somewhere, so from here. So make sure you contact me if you want to know more.
Yeah, sure, sir. Thank you. Now it's the time to express my gratitude to all. On behalf of ECE Department, St. Joseph Institute of Technology, St. Joseph Group of Institutions, my first and foremost thanks to our guest speaker, Dr. ZEID KOOTBALLY, for taking time to giving information on robotic simulations. And my heartfelt thanks to our beloved chairman, sir, Dr. B. Babu Manogaran, for his constant upkeep in conduction of this webinar. My sincere thanks to our managing director, ma'am, Mrs. B. Jesipriya, and our director, sir, Mr. B. Sashishekhar, for their guidance in the conduction of this webinar. I would like to express my gratitude to our principal, sir, Dr. P. Ravichandran, for his support to conduct this webinar. I also thank our head of the department and IEEE chapter advisor, Dr. C. Jnana Kausalya ma'am, staff and student affairs, and Dr. G. Rogini ma'am, IEEE coordinator, head of lab affairs, for their words of encouragement and guidance. And I also take this opportunity to thank the entire fraternity of St. Joseph Institute of Technology, St. Joseph Group of Institutions for making this event a memorable success. Finally, I thank all the students, faculties, and research scholars from India and other countries for their active participation in this webinar. Thank you all. Our next webinar is on optical coating by tomorrow. The registration can be done through the same link. Thank you all. Have a good evening.
Thank you.
Thank you, sir, for the more informative session. I hope that